Hello, I think I'm. Yeah, it looks like it actually has started. So welcome to the qualifying for, which is my first time on YouTube, which is, I think, MBL. It's first live on YouTube ever, so it's a historical moment for YouTube. And yeah, the plan for today is I'm gonna discuss 8 problems we had at the qualifying quiz this year. Okay. If I hope that I'm being heard. If I'm not being heard, please comment. But hello to everyone that already said hello in the chat. Feel free to ask any questions in the chat. I might have a look at. Sometimes lags out. Okay. I'm not sure if. Yeah. Okay, maybe after a while it's gonna get better. So first of all, congratulations to everyone who applied. We did send application results a couple of days ago, but we got a lot of very good applications this year. So it was a very hard decision. And we got a lot of nice quiz solutions too. So I feel like I need to sort of underline at first that we do look at many different things in the application. So it's not like if, even if you solve all the questions, but a statement, you probably won't get to the camp. Of course, this is not the case for everyone has written some personal statement. No one has solved all the problems. The problems were quite hard. But feel free to ask any questions in the chat, but I probably will not be able to answer any questions regarding specifically the admissions, or I might struggle to answer them. I will be very happy to answer any questions about the problems. Now will try to share my screen. Which I hope has been done. Okay, so let's get to work. We have 8 problems to solve. So the first one. Let's start with red. Why not? It's like red, but like a bit purple. Okay, so in the first problem, we have defined S of n to be the number of sum of digits of n, and we got in the problem is some AB positive integers, and the question is, are there x and y positive integers such that S of so if we take the sum of digits, then the sum of digits is going to be A, and if we take 10 times one number plus y, then we get a B. Sum of digits equal to B. So if we, I don't know, if we get x 27, y 38, because why not? When we calculate x plus y, we get 27 plus 38, and it's gonna be, that's hard. That's like the hardest thing I ever solved since, I think that's 65. Do let me know if it's not, really not sure about x. 10 times x is gonna be 270, but I will like purposefully write, for ideological reasons, I will skip the 0. So sort of we use the same digits. Everything is just a little 308. And in this case, the sum of digits is 11. And in this case, the sum of digits is 11. And in this case, the sum of digits is also 11. So connection. I'm seeing a few issues in the chat. Is everything actually working, or is it not? Okay, I will just continue. If you do, if someone could write me that okay. So the whiteboard did. I mean, I can see my whiteboard on the live stream, so I feel like that probably would mean that everyone can see it. Hopefully. Maybe I should write smaller things. If I just take a smaller pen, maybe. Okay, we'll see how it works. Okay, so first of all, I mean, probably the answers depend on these numbers A and B. Probably we want some kind of restrictions on them. So what can we say? Well, we use the same kind of digits, and what can we get from digits? Well, there are divisibilities by 9. So there's this fact that S of n, well, okay, might be S of m, and m give the same remainder when divided by 9. And so, in particular, what will happen here is that because x plus y gives the same remainder modulo 9 as 10x plus y, well, because their difference is divisible by 9. It's 9x. Therefore, the sum of digits of x plus y will be the same as the sum of digits of 10x plus y. This is A, this is B, modulo 9. So we get some restrictions. So we actually know that, okay, for the problem to make sense, I mean to get these numbers x and y, we need to, for A and B, to have the same remainder modulo 9. Okay. Apparently the whiteboard is not visible, like at all. If you could let me know. Okay, I'm not good into computer science, so I will do what I can. I will just stop and start again. Is that better? Yay. Okay, so okay. Finally, I did some positive feedback from the chat, so great. Old trick of turning off and turning on. Okay, so let's go quickly through what I actually did right. So the problem statement is we define S of n to be the sum of digits of n. We get some two integers a and b, and we are wondering if there are x and y such that x plus y has the sum of digits a, while 10x plus y has sum of digits b. And then I did go on about sort of 10x and x having the same digits, sort of, because 0 is, well, 0. So if we just write 0 as, I mean, we will ignore 0 in this notation, then sort of we get the same digits on the entry. And we are wondering, like, if we shift things, what kind of effect can it do? Can it have on the sum of digits? Okay, so in this case we got 11 and 11. That was not very fascinating, perhaps. But then we can use the fact that S of m and m give the same remainder when divided by 9. And from that we get that if a and b actually work, they have to give the same remainder modulo 9. Okay, so that's sort of the big chunk, the huge chunk of an idea here. Can we get everything though? So if you try to experiment, well, so sort of now we just need to construct an example for each pair a and b such that a and b have the same remainder modulo 9. And if we try to do it, well, the first such pair is a and b equals 1, 1. And then you're in trouble, it turns out, because if you try to do it, then nothing works. Why? Well, a simple explanation is that your 10x plus y is strictly bigger than x plus y and strictly smaller than 10x plus 10y. But numbers with sum of digits 1 are just powers of 10. So if x plus y has sum of digits 1, that means this is some power of 10, say 10 to the m. But that means that 10x plus 10y is 10 to m plus 1. So 10x plus y lies between two consecutive powers of 10. So it can't be a power of 10. So we actually get no solutions. No solution here. Okay. And if you do further experiments, then it turns out that actually everything else works. And yeah, you can sort of brute force it. You can try to just compute like an example for every pair. This is probably not very, I mean, possible, definitely possible. What I was thinking about, I mean, two options. My first thought about when I was solving this problem was there are a lot of such pairs. So maybe if we could find a way to combine two pairs like that. So I claim if A1, I'll write a claim. If A1, B1 works and A2, B2 works, then A1 plus A2, B1 plus B2 works. So how do we do it? Well, if this is working, then let's take x1, y1, such that S of x1 plus y1 is a1, and 10x1 plus a1 is b1. And similarly here, and the idea is we can just combine the solutions together. So what we can do is take x to be x1, then a bunch of zeros, then x2. And for y, we take y1, a bunch of zeros, and y2. And we basically just care for these numbers to be like aligned. So x1 and y1 need to end at the same point. So we sort of use the numbers, like align the numbers of zeros so that x1 and y1 are over the top of each other. So then how will x plus y behave? Well, x plus y will just, if we add them just together, then we get, if we go from the right, we get x2 plus y2 at the end. Then we get the same bunch of zeros. And then we get x1 plus y1 at the beginning. And very similarly, if we do 10x plus y, then we have 10x plus 1 here, and something like this. This is sort of vague and probably should be made formal. But the idea is that we can use a bunch of zeros to separate two situations so that they will not interfere with each other, nothing breaks down. And then the sum of digits of these two numbers will be just the sums of the blocks we have used. Okay, so this way we can just generate like some pairs, examples of some pairs, and then all other pairs we will just get by adding these small examples together. Because yeah, we can also see that we can use the claim multiple times. If we have 5 pairs, then we can do the same, but with like 5 blocks, 4 sequences of zeros between each other, and it will also work. Yeah, so now we just need some sort of minimal set of pairs that will generate all possible pairs. There are some fancy theorems, like fancy terms like Hilbert basis or something like this, to do it like in abstract maths. But we can just, I guess, write down something. So what we need is, okay, if A and B are equal, then I guess we need 2 and 2, and probably 3 and 3. It's unfortunate that we don't get 1 and 1, because that would be very useful for us in this summing idea. And then from 2 and 2 and 3 and 3, we can get every pair of form AA just by adding, well, 4 and 4 is 2 plus 2, comma, 2 plus 2. 5 and 5 is 2, 2 plus 3, 3, and so on. Okay, and what about the differences? Well, we can, it will be enough to have something for 1, 9k plus 1 and 9k plus 1.1. And again, unfortunate that we don't have 1, 1, because we will also need something in those cases. For every k greater or equal to 1. Yeah, and you can check that. I I mean, sort of from those you get every possible difference, and then by just adding 2 and 2 and 3 and 3, you can get everything with a suitable difference, anything that you want. And yeah, you just need to write down some examples. 2 and 2 will probably be easy. That will be 1 plus 1. For 3 and 3, that will be probably 1 plus 2. And then it's sort of a bigger struggle for those, especially given that you have 9k plus 1. So, but yeah, I mean, the idea will be basically take 999 and then 1, right? Something like this. And then if you add this up, then you get just a power of 10. So the sum of digits is 1. But if you add a 0 here and add 1 here, then you get 9k plus 1. And, you know, a game like this. It's also possible to do the same for the rest. Another way to approach this is if you're very lazy. I am meanwhile struggling to use a whiteboard. What's going on? Oh, I'm sure. I did not. Oh, please. Okay, I will do the same as I have done today already, and it's worked. I will turn my graphic tablet off. I will turn this on. Did not work. In fact, does not work at all. Okay, it seems that the age of 22 is already being too old to actually know how computers work. Yeah, great, something happened. Or not. Really? Is that at least possible to erase? Okay, that's something. So another way is if we don't want to construct things, we can just tell that they are there somehow. What do I mean by that? What do I mean by that? Well, let's just write something down. We have these numbers x plus y, and we have this number 10x plus y. So let's say this is m, this is n. So now we want s of m equals a, s of n equals b. That's a break for a t. And if we forget about x and y altogether, and we could just choose m and n, then surely we can just write a number with sum of digits equal to a, a number with sum of digits equal to b, and that will be it. It's not going to be interesting. So what kind of pairs of m and n we can get? Well, we did observe before that m is smaller than n is smaller than 10m, and that m and n are the same modulo 9. And I claim that those are actually only two things we need. Why? Because this is just a system of equations and we can solve it. And we will get x equals n minus m over 9 and y equals 10m minus n over 9. And we see that both are positive because of the P's inequalities, and both are integers because of m equals n modulo 9. So we just need to find two numbers satisfying these conditions, but we also know that, well, m is the same as a, n is the same as b modulo 9, and we want to take a equals b modulo 9. So we don't need to, like, if we restrict ourselves to the pairs that work, we don't need to worry about right-hand side at all. And for the left-hand side, the way I was thinking about it is if m and n have the same number of digits, same number of digits, then 10m is automatically greater than n because it has more digits than n. So we just need n bigger than m. So we need a very small number with a sum of digits equal to a, and a very large number with a sum of digits equal to b. We don't even have any restrictions on the numbers of digits. We can just do whatever. So yeah, for instance, I mean, an easy way to do it is take n to be, this is not a very big number, but it will be enough. Just take b digits like here, b1s, and m to be 1 and then 0 and then blah blah blah, and you have a minus 1 ones at the end. So you get s of n equals b, s of m equals a, and you get n bigger than m. And if you choose your numbers of zeros suitably, then you get that these have the same number of digits. So, so 10m will be bigger than n. Great. And sort of now you can just plug in, solve the system of equations, get x, y, and you're done. So somehow, yeah, you don't even need to think about adding things here. I mean, especially not think about adding things and then how will sum of digits behave, anything like that. So you just write it down and you're done. Okay. I guess I will need to speed up. Oh, I don't know. I mean, this was sort of, it was problem number 1. So a lot of people approached it. I'm not sure if it's not the quickest solution ever, because you need several steps, and the construction will be you need to do something, basically. But hopefully, if you start doing things, then maybe you will get somewhere. For the problem number 2, I'm not sure if that's the case. You need an idea to move on, perhaps. So what's the problem? We get a graph of a function. Okay, good enough. And we know that if we draw a line, I'll take orange. If you draw a line, and if we have the parabola of y equals x squared, and we draw the same line, then in these two cases, we get the same number of common points. Okay, and we are wondering what kind of functions satisfy this sort of statement. It's not hard to figure out that probably if you take x squared, then that's gonna work because those will be the same picture. And after you play for a bit, it turns out that, yeah, maybe this is the only example, which would sort of make sense. But how to do it? Let's make some space. I think I don't know. Let's go back to the green. So we have those two pictures. We have the parabola, and we have this f of x, which, to be honest, we don't really know how it looks like. So we want to get some information, and what kind of information can we get? Well, the information we get from the problem. So just take a line, look what happens. Okay, and basically there are two steps in the solution, I mean, in the model solution at least. Claim one is that f of x is bigger or equal than x squared. How do we prove? Well, suppose if not, then for some x, we get f of x smaller than x, maybe some x0. Okay, and how does it look like on the left picture? We'll get a point on this somewhere here. So if we have parabola here, then somewhere like here. So okay, and we know that every line intersects the graph in the same number of times on the left and on the right. But if we just take a line through our point, then it will intersect our graph on the right-hand side. But since the function x squared is convex, you can always choose a line that will not intersect the parabola on the left-hand side. If you're a person that needs examples, then your line that you can take is y equals 2x0 x minus x0 plus y0, where y0 is this guy. And you can check that actually for this, you always get that this is smaller than x squared. I mean, actually, it's not even like, okay, geometrically, the parabola is a convex set. I mean, inside of the parabola is a convex set, so you can just draw a line outside of it. But even algebraically, if you just you want to prove a thing like that, how do you prove it? Well, just by rearranging. You put 2xyx and 1 of x not squared to the right. You're left with y0 and the remaining x0 squared here. And this we want to be lesser than or equal to x minus x0 squared, it turns out. But this is true because this is smaller than 0 and this is at least 0. Yes. Okay. So claim 2, f of x is equal to x squared. And again, getting back to the picture, suppose we have an x somewhere, maybe here, on the parabola, and now we want to say that it's on the right-hand side. But if we draw a tangent to the parabola, then, okay, it has one common point with the parabola. And how many? So one common point with our f of x. But we know that, well, basically from this claim, we know that the whole graph is contained within the parabola. We don't know yet if it's the parabola, but we know that it's somewhere here. In particular, if you draw this tangent, then we already know that none of these points, like non-orange points, apart from this point, can lie on the graph of your function. But we know that there's one common point, so there should be one common point. So this common point is actually also on y equals f of x. But you can do it for every x. So this point is like the whole parabola needs to be on the graph of your function, which means that your function is the parabola x squared, which ends the problem. Yeah, I always sort of want to like I want to keep coming up with nice problems. This is not my problem, but I mean, this if you want to, then it does turn into a nice research problem. What happens if we take y equals x cubed, let's say? I did try to solve it for a while. I did get some progress, but I did not get a full solution. So you can think about it. Basically, you can think about like any polynomial. Like, can we recognize any polynomial using something like this problem? I mean, for sure, if you take x to the fourth, then sort of the same method works because again, your graph is convex, is just more pointed. But about x cubed, I'm not sure. So if you want to think about something like that, I mean, there are sometimes contests, like research contests for high school students. So if you're looking for a topic, then feel free to use any MBL problem you like. All right. I'm looking for reactions from the chat. Okay, no one is complaining about the problems too much. The problem number 3. The problem number 3 was about Fibonacci numbers and what's better than Fibonacci numbers in mathematics. So we want to color numbers. Well, we have Rn. I do like 0, so I will write n plus. It starts at 1. So we want to color in 2 colors so that if you take, let's say, if you take a blue number and if you add it to a red number, is never, this will be never a Fibonacci number. Where Fibonacci numbers, as you probably know, you start with 1, 2, 3, and then everything next is just the sum of the two previous guys. So it goes like this. Okay. So yeah, well, maybe for an example, we can try to go with, a couple of steps. So without loss of generality, the first one is blue. Okay, but now I did mess up. Of course, we mean that two numbers of the same color can never be a Fibonacci number. If that would be with two numbers of different colors, then yeah, it's not true. Okay, and we get two colors though. Okay, so now 2 has to be red because 1 plus 2 is 3, which is a Fibonacci number. Then similarly, 3 is blue because 2 plus 3 is a Fibonacci number. 4 is red because 1 plus 4 is a Fibonacci number. But 5 is also red because 3 plus 5 is a Fibonacci number. And then you get, to sort of accelerate a bit, 6 is blue, 7 is red, 8 is blue, I believe. And then 9 is blue, 10 is red, 11 is blue, 12 is red, and 13 is also red. So it's okay. It looks like sort of an irregular pattern, and it's, I think, fairly irregular. So how do we solve stuff like that? So I will just sort of for your entertainment value. There is something called degeneracy in graph theory, and it doesn't help here, but sort of the intuition does. So we say that, do I remember the notation for degeneracy? Well, I'll just write D of G is S most M. G is your graph. If we can arrange vertices from left to right, so that every vertex has at most M edges going left. Okay, so how do graphs with degeneracy 1 look like? So you get a vertex. Okay, the first vertex is not very interesting. The second vertex can be connected to something on the left. The third vertex can be connected to something on the left, but only one such thing. 4 vertex similarly. And we can basically make pictures like this, on and on and on. So basically, it turns out that graphs with degeneracy 1 are precisely trees or forests to be, to make disconnected graphs happy. And like a standard idea in graph theory, which you didn't need to know any of this to actually solve the problem. I'm just sort of presenting the idea behind the problem. All right, and yeah, it's like at most here, but then the degeneracy is the lowest you can get, lowest m you can get. And there is a lemma, I guess. Graph G is always colorable with D of G plus 1 colors. Okay, and how do we do it? Well, we can choose a picture like this. Well, for D of G equals 1, we can choose a picture like this, and we can just, well, go from left to right. So, okay, the first, let's say the first is green. Then the second one is red. Then the third one is connected to the red one, so it has to be green. The fourth one is also connected to the red one. Now the fifth one is also connected to a green one, as well as the sixth one. And yeah, you can easily see that in this case, since we only have one edge to the left, we only have one forbidden color. We are using that we have a nice ordering on the vertices. So for instance, this guy here has 1, 2, 3, 4 edges. So if we colored everything else and then try to color the guy, then we could have like 4 forbidden colors, and then we could be stuck. But if we are going from left to right, then we're fine. Okay, so unfortunately, this idea doesn't work in this problem. So you can construct a graph in this problem, and it turns out that it has degeneracy 2. And we would like to have degeneracy 1. But the idea still works. So the solution and we just proceed by induction. I mean, it's sort of induction, I guess. But we just want to show that we can always color the next vertex. I mean, the next number, going from 1, 2, 3, 4, 5, and so on. We can always color the next number. We always have a color. So we already have seen how it looks for the small cases, so I will not try to write any basis of induction or anything like that. I just need to yeah, find something. Yeah, find the color for our number. So let's suppose we have some x, and x will be between 2 Fibonacci numbers. Necessarily. So let's say we have some fn here, and we have some fn plus 1 here. Okay, so we want to give color to x. So what kind of edges does x have going to the left? So what are y's such that x plus y is Fibonacci, and y is smaller than x. I mean, we can have x plus y equals fn plus 1, I guess, we can have x plus y equals fn plus 2. Can we actually have fn plus x plus y equals fn plus 3? And I want to say that no, we can't. Why can't we? Because fn plus 3 is fn plus 2 plus fn plus 1, which also is, if we break down fn plus 2, which is 2 fn plus 1 plus fn, but x was smaller than fn plus 1, so this is bigger than 2x, and in particular, this is also bigger than x plus y. So we actually, this can't be true. So we have only two cases which we want to worry about. And sometimes we don't actually need to worry about both of those cases. Because, well, for instance, if x is 4, then here we get basically 1 and 4, but we don't need to bother about 4. There are no edges to a number itself. I mean, even if there are, then those numbers have the same color, so it's not great. Yeah, so I probably should have said distinct at some point when formulating the task. Right. Okay. But yeah, I mean, it can be an issue. So we basically know that x needs to have a different color. With I will denote this by an edge because of graph theory. We know that x and fn plus 1 minus x have different colors. And we also know x to have a different color from fn plus 2 minus x. Okay, so if that is bigger or equal to x, then we actually don't need to worry. We can just, I mean, this is not an edge we see at this point. So we just color x with a different color than this guy here. And we're done. And we can proceed by induction. What happens if this is smaller than n? Sorry. So smaller than x, sorry. Well, if those two numbers have different colors, then it's not looking great. So we want them to have the same color. And actually, they have the same color because those two colors are different from the color of x minus fn. Right, because sum of these two numbers is fn plus 2 minus fn, which is fn plus 1, which is a Fibonacci number. And sum of these two guys is fn plus 1 minus fn, which is fn minus 1, which is a Fibonacci number. So if this number was blue, then if we color x to be blue, then we know that these two numbers are actually red, so we can just make x blue and everything works. So sort of we can use this step back to actually get that that x indeed, I mean, that but the coloring will be fine. So sort of the idea is the similar as in the degeneracy theory or something like this. But now, because we sort of get a lot of these for cycles, we can actually do one better. Okay, what is sort of interesting about the problem, I guess, is that this gives us essentially one way to color all these numbers. So basically, if you have an idea of your coloring, if it gives something different than what I have written down here, then sorry, it's probably not working. This is if you put either blue numbers or red numbers to the online encyclopedia of integer sequences, then it's a sequence there. And it turns out that you can define it using the golden ratio somehow. Basically, I think, yeah, if I think the idea was sort of that n is blue if you multiply n by phi, then you need to round down your number to get an integer, and it's red if you need to round up your number to get an integer. And probably it's somehow possible to use this in this problem using probably something like Binet formula for a Fibonacci number, but it's probably going to be a bit messy, but probably at least will give you an explicit construction of do this to get your solution. All right, let's move on to the geometry then. To all geometry fans out there, yeah, I'm sorry, I got a lot of feedback that this was not a very hard geometry for people experienced with geometry. Which is perhaps a good moment to say that if you'd like to submit some problems for MBL quiz in the future years, feel free to do it. I always appreciate help. If you have been to a MBL in the past and you're not applying as a participant, then of course that's fine. If you're applying as a participant but still would like to submit some problems, then that's actually fine. I mean, I guess that participants that come up with their own quiz problems are like even better than participants who solve what we are giving them. So we'll see. But yeah, I do ask you for contributions if you're out there and if you have a problem that you would like to give for MBL, then please. Especially geometry. But like everything's fine, really. What's the geometry then? We have a triangle, as geometry usually does. We have a circle, which I foolishly did not draw at the beginning, but which doesn't look very bad, I guess. And we have some points. We have A, we have B, we have C, we have M that is the middle of an arc. We have N that is the reflection of M across BC. And we also have the orthocenter of our triangle somewhere here. Okay, this doesn't look too good. But for some reason, Ctrl+Z doesn't work for me. Yeah, perhaps more like this. Yeah. Yeah, this was a very convenient attitude from A. that just goes to the left when it has to. And what we want to prove is that Hn and Am are perpendicular to each other. So perhaps one quick comment. When I was writing the problem, I wrote that M is a middle of arc BC. I did not write which arc BC. So there is also another way of drawing this with M prime here and N prime somewhere down, which will also work. But also, like, I think every solution which works for one case will probably work in the other case with not much change. How can we do it? We can notice one nice point here, which is the middle of the side BC. I will write it as S. Well, okay, let's spoil the problem. We can reflect H across S. And it turns out that this is precisely the point that is opposite A on the circumcircle. Why, you may ask? So I will quickly sketch the proof on the side. We don't need M here, so we just have H somewhere. And we have the reflection point somewhere. And what we want, we probably want to compute some angles, right? What kind of angles? How was it actually proved? All right. Will that be that easy, or am I doing? No, okay, probably it won't work. So let's start with reflecting H across the side BC. We claim this lies on the circumcircle, and then we will reflect it across the midpoint, and we will claim this lies on the circumcircle. And that it will be the opposite point. So first, why that guy? We want to check some angles. I guess we want to check that this angle is the same as this angle. But what's this angle? Well, because we reflected, this is the same as this angle. And now we have 90 degrees here. We have 90 degrees here. So if we have some gamma here, then we can notice that this is 90 minus gamma, and this is 90 minus gamma too. So these two angles are actually the same. And so this H prime here lies on the circumcircle. And now if you if we reflect it across the perpendicular bisector of side BC, then because this bisector goes through the circumcenter, so the reflection, I mean, the circle is symmetric with respect to this this line. So if you reflect it somewhere here, you get H double prime. And now I say that I want to say that this is actually the same as reflecting across the midpoint. Well, why? Because basically we will get I mean, a right-angled triangle, and in right-angled triangle, you get the fact that this intersects this on the midpoint of the side, of the long side. But we know these lines which, with respect to which we are reflecting. One of those lines is BC, the other line is the bisector of BC, so they intersect actually in point S. And now one last part is why H double prime is opposite to A on the circumcircle, but we have this right angle here, so so we have that H double prime is a diameter. Probably there's a faster way to do it, but at least you got to see that H prime also lies on the circle, which is also a very useful fact. Right. This is also like very useful if you want to prove some facts very quickly. I mean, probably from something like this, you can get quickly that H and OY are isogonal conjugates in the triangle, if you know what isogonal, if you care about isogonal conjugates and you know what it is. Okay. Okay, I have a comment from Michał. Let me analyze. A prime C is parallel to BH. It is, which is, yeah, ACA prime, also ABA prime. A prime C, right? Yeah, okay, that's another way of doing it. Very nice, thank you. So if we just want to reflect it, just use the reflection, then we have H that is reflected somewhere, but we can reflect the whole segment BH as C and then H double prime. But the reflection will be parallel, so actually, and well, we have the right angle here, so we need to have right angle here. And then similarly on the other side, this is perpendicular here, and this will be this. Basically, we have a parallelogram here, so we have right angle here. And we have two right angles, so we get that they all four lie on the circle because of the sum of the angles is 180 degrees, and H double prime is a diameter. Okay, but coming back to the problem, if we know all that, then the problem is quite quick. We can notice that, okay, N is reflection of M across BC, but this is the same as a reflection of M across S. We know where reflection of H across S lies. So in particular, this HN is the reflection of MA prime with respect to S. But we know that AA prime is a diameter, so AMA prime is a right angle, and MA prime is parallel to HN. So it's also perpendicular to AM. End of problem. So the solution wasn't very, very long, but it's, I mean, you needed the idea of reflecting something across the side. I had another solution, much more complicated, but that was sort of how the problem was born. So I will show it just for the sake of this, and for the sake of showing even more random facts that is useful. So you can reflect M across BC to get N. You can reflect M across AB, and you can reflect M across AC, and you get 3 points. And there is a fact in geometry called the Steiner line that these 3 points will be lying on one line. And also on this same line, you will find H. Okay. A nice fact. You can think about the proof. I don't remember the proof. It's probably not very complicated. Probably follows from stuff like this. Probably, I mean, you do reflect H across the sides. You get some points on the circle. You need probably to carry some angles around. But basically, what the Steiner lemma can say, can help you with, is that instead of looking at the line HN, you can look at the line between those 2 points. How can I call them? X and Y. That are like completely 2 different points, but you can, at least you can get like X and Y. Maybe it will be easier to prove something about X and Y. And now we want XY to be perpendicular to AM, but AM is the bisector of this angle. And X and Y are symmetric with respect to this bisector, because M lies on the bisector. So basically, the picture you get is you have an angle, you have a point on the bisector, you reflect it across 2 sides of an angle, and you want this to be perpendicular to this. So you see that everything is completely symmetric. So it's perpendicular. So yeah, that was using a random fact about Steiner lines. To be honest, I'm not sure if anyone solved it like that. Probably even a complex bash would be easier here. We are already going like, I thought the time will be better. So I'm not going to show the complex bash, unfortunately. We'll just get straight to the problem number 5. All right. Problem number 5. So yeah, for the problem number 5, I sort of, I sort of thought, okay, it's problem number 5. It can be as hard as it can be. No one will know this. And yeah, people probably found it harder. I thought it's gonna be a bit hard. We did have a huge disproportion in the number of solutions submitted. But no one did get the solution I had in my mind, at least not well explained, at least. So what was the problem about? We get a family of convex polygons, or actually 2 families of convex polygons, but they can be also degenerate ones. So we can have some segments and points lying around. And what we know about this number of what we know about these families is that every point on the plane lies in the same number figures from both of these families. So let's say family A and family B. And now what we want to prove is that these 2 families have the same number of elements. So ideologically, we know that at every point, like locally, these families are the same, like equal number of elements at every point. So we want to get something like equal everywhere. All right. Maybe first to show that this problem is not trivial and it's maybe interesting, and example of two families which work, I'm going to take two triangles with a common side. So this is my figure 1, this is my figure 2. And now I'm going to take a triangle that is the sum of these two triangles. And this is my figure 1. Oh, wrong place. Because I'm going to also draw this segment here, and this is my number 2. So if you analyze it, what we get is that every point in both of these figures lies in exactly one figure, apart from points on the line on the segment, which lie in two figures. So we have equality. We have like different dimensions, sort of. So on the left, we have two triangles. On the right, we have a triangle and a segment. But we get the same number of figures in total. All right, so my idea to solve this problem was we want to do something for n equals 2 here to show something on the plane, but actually we can do it for every n, and this makes stuff easier because we can use induction. So basically, we will use induction to show a statement for a 2, which is nice. So okay, so proof by induction. So let's start with one dimension. How do one dimension works? So the same problem in one dimension, we'll have a line. And on the line, we have a family of segments and points. Again, so that everything is in the same number of figures from both of those families, and we want to prove that they have the same numbers of figures, which are now, again, segments and points, or points. But lines are easier than planes because we can just go from left to right. So we can take a look at the leftmost part of the blue figure of blue figures. Take any blue figure that has something there. Now take, well, this point also has to lie in some red figure, so take any red point that is in some figure over here. And if both of those are segments, well, okay, first, if both of those are points, we can just cancel them out. So we can just throw them out of families, and we'll be happy. If both of those are segments, then we can edit this. So throw something out. I mean, instead of those two segments, we take a segment here and the red point here. Okay. And then you can see that, like, we just reduced this, like, reduce the figures by the same sort of part, which is a segment which is closed on the left, opened on the right, open here. So everything stays the same, the number of figures stays the same, and we have reduced the figures. So we sort of do it algorithmically. So what can break down is, okay, if we have 2 points on the left, we're fine. If we have 2 segments, we're fine. What happens if we have just segments in the blue, and we have just points in the red, because then we can't really reduce anything. But then if we have a couple of red points, well, with multiplicities here, and a couple of blue segments, maybe one, then we can just, well, the next part of the next red figure will have to start somewhere. So we can take a look at a point in between. And this gives us a contradiction because there are no red points. I mean, this sort of, imagine this squashed on one line. This point does not lie in any red figure, but will lie in a blue segment. Contradiction. So we can always reduce our picture like this, and it's yeah, you can prove, I mean, sort of in each step we reduce the number of segments. So we will be done in finite time, and after finite time we have canceled everything out. So these are equal. Nice, everything's done. All right. So we're done with the case of d equals 1. How do we proceed for d equals 2? Well, I claim that what we can do is take a line, and we can just project everything onto the line. So instead of having a blue figure like this, we get a segment like this. Segment. And I claim that this family of segments also satisfies the problem. Okay, why is it so? Well, how many blue figures, like after the projection, take a point on your line? How many blue segments is this point in? Well, this is the same as the number of the blue figures this line intersects. Okay, and for the red similarly. So we have a line, and we want to say that this line intersects the same number of blue figures and red figures. But now we can just look in the other direction. So we have some blue segments. If we intersect, we get some blue segments and red segments here. And we know that every point is in the same number of blue and red. So along this line, we need to have the same number of blue and red figures. But the line only sees the intersection. So we intersect the same number of points. So we have used our inductive assumption on d equals 1 to, so now after the projection, we get a family of well, segments and figures. And after the projection, we are back to the one-dimensional case. So everything works fine. And now we get from one-dimensional case that the number of figures in total is equal. Quaderat demonstrandum. So yeah, this is kind of tricky because we can use this one-dimensional case to actually reduce the problem, but we need to reduce it somehow twice to get d equals 2. Especially the intersection idea is sort of non-trivial, but it works. And this way you can actually prove the statement for any dimension. So if you want, you can solve the problem in 7 dimensions. Paradoxically, probably solving this problem in 7 dimensions is easier than in 2 dimensions because you can't really draw anything in 7 dimensions, so you need to use an idea like this to reduce. And in 2 dimensions, people were doing quite well in trying to come up with some geometric arguments of, well, okay, this vertex is looking like this, and then maybe this side, and maybe if we calculate the angle, then something happens, and so on. So yeah, this was quite complicated. But yeah, but we are done with first 5 problems. Wow, great. 3 problems to go. We still have 11 viewers after 90 minutes. Wow. Thanks for watching. I'm not sure if, yeah, my first time as a YouTuber, so I'm not sure if I should say, leave a hand up and subscribe to our channel. But do subscribe. Also, if I'm doing a little break, then tomorrow is the deadline for the tutor application. So do apply as a tutor if you want to. Right. Problem number 6. Problem number 6. Now we go into the area of exploratory problems. So I'm going to probably pick up the pace somehow because it's more about ideas than solutions, and I don't always have solutions. But this was very age appropriate year appropriate problem. Yeah, that's what I definitely was trying to say. So it was born of a meme I saw that, wow, 2025 is such a special year that you can do this. You divide it in half, you take a sum, you square it, and then you get back your number. And my question was, what can we say about these kinds of behavior? And we did ask you a couple of different questions. So I'm just going to sort of rotate along them. But the main idea is, the main idea I had, at least. To be honest, I might need to go for a charger to my laptop at some point, but I think I'll do this and maybe go then. Yeah, because I will probably need then to change the setup, and I like to, I especially booked this room at my university just to have books in the background, because I heard it's popular to have books in the background, so I have books in the background. Right. So what can we do? Well, we can say this is x, this is y, and we are solving some equation. What kind of equation we are solving? This is x plus y squared equals, well, here it will be 100x plus y, so I will maybe go through, well, maybe not, you're brave people. We can go for a general case. So if the part corresponding to y has n digits, then we are actually solving x plus y squared equals 10 to the n times x plus y. All right. And how do we solve it? Well, this is a quadratic equation in x, I guess. I mean, also in y, but also in x. So you get something like this. minus y equals 0. And you basically just need to solve in terms of x, and you'll get some answer for x, which will be in terms of y. Okay, let's see. This is our x term, right? So we'll get. Haven't done it in quite a while. 10 to n minus 2y, I believe, plus minus the square root of this squared minus 4y squared minus y. Sure, over 2. This is our x. And what we want to happen is for this x to be an integer, which is not entirely obvious. I mean, what we can notice is that at least it's if the numerator is integer, then it's even because everything here is even. So we could divide by 2. We can also notice that the square root has something smaller than, I mean, the square root is always smaller than 10 to n minus 2y, because it's the square of that minus something positive. So this is always strictly positive. Strictly? Well, non-negative. We will have equality with 0 if y is 0 or y is 1, which is precisely where this term y squared minus y is 0. So yeah, I mean, this is at least 0 if y is an integer, because if you take y to be a half, then it's not looking good. All right, but when, okay, so basically we just need to figure out when this delta here is a square. And what's this delta? This is 10 to 2n minus 4 times 10 to n y plus 4y squared. Sorry, minus 4. No, yeah, plus 4y squared minus 4y squared minus plus 4a. Great. So 4y squared cancels out, and we get that this is 10 to n minus, and here we get 4 times 10 to n minus 1 y. All right, and we want this to be a square. But this is even, so we can divide by 4, and we want this to be a square. 10n minus 1 y to be a square. But all right, what can it be if, like, we vary y? I mean, obviously we want it to be non-negative, I guess, for it to be a square. Y will be positive, so sort of this is bounded by 10 to n over 4. How can we get a square? What squares can we get? But we can observe as y varies, then basically this is any number which is equal to this 10 to n over 4 modulo 10 to n minus 1. Right. Okay, and what I claim is that actually I mean, I actually will get many squares like that. And when you have a square, yeah, suppose it's something like s squared, I guess. I mean, so you want s squared to be 10 to n over 4 mod this. You know that s squared has to be at most 10 to 2n over 4. So you know that s is at most 10 to n over 2. All right, so you're just solving this congruence, which might be, okay, hard, but probably is doable. I mean, okay, you have one answer of taking s to be equal to 10 to n over 2, for sure. So at least if you have an answer, then sort of you know that it's nothing like, you know, x squared equals to modulo 3. It will be solvable actually, and you don't need theory of quadratic residues or anything like that. So I claim that if our 10 to n minus 1 has prime divisors p1 is it writing? Okay, yeah, it's lagging a bit, but I guess it's my fault for using Microsoft Whiteboard. If it breaks down as a prime factorization this way, then basically we want any solution for the congruences of s equals plus minus 10 to n over 2 modulo p1 p1 alpha 1. So I want to say that if and only if s satisfies this set of congruences. And why do we like this set of congruences? Well, because P1 alpha 1, P2 alpha 2, blah, 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 are pairwise coprime. So we can use Chinese remainder theorem. And the Chinese remainder theorem will tell us that we have exactly one solution from 1 to the product. The product being 10 n minus 1. So CRT gives us so S has to be in this interval of 1, 10 to n minus 1. Okay, but we wanted S to be at most 10 to n over 2. But very conveniently, this is exactly the midpoint of our interval. And it turns out that if S satisfies this congruence, I mean, this set of congruences, then if we swap every plus with minus, then 10 to n minus 1 minus s will also satisfy, I mean, symmetric set of congruences. And so basically for exactly half of the choices of plus minus, you get a correct choice. So you'll get exactly 2 to k minus 1 solutions. So, wow, solutions. Which, wait, is not true because it's not the only choice we could have. We actually had this other choice of plus and minus here. So this times 2. So in the end, we are getting exactly 2 to the number of distinct prime factors of 10 to n minus 1. So this was, I think, part D of the problem. So I think the hardest part of the solution is figuring out that, I mean, it's hard to make a conjecture because you'll get, so I will comment in a sec why one of those solutions will actually not work, and then you'll get 2 to k minus 1. And then it's sort of hard to figure out from the sequence of results, like 3, then 3, then maybe you'll get to 7, but if you probably code it down or you're very good at computing this stuff by hand. So it's hard to make some sort of conjecture, but it will be like number theoretically connected. Okay. Okay, why is it true? This thing, it's not that hard. I can probably, if I erase this, I can fit it onto a margin, which is always a nice thing to say in number theory. So why? Well, if we go up, then we get that if S satisfies all these congruences, then S squared gives 10 to 2n over 4, modulo each of those guys, so modulo the product, which is 10 to n minus 1, we're done. How to go down? Well, we can just restrict, I mean, if it's true, then it's also true modulo NEP I to alpha I. And then, well, when do we get a congruence? Well, if the difference is divisible by our modulo. What's the difference? The difference is S squared minus 10 to n over 4, which is the same as S minus 10 to n over 2 times S plus 10 over 10 to n over 2. And what you can notice is that actually, if one of those guys is divisible by pi, then the other guy is not, because their difference is 10 to n, and pi divides 10 to n minus 1, so it can't also divide 10 to n. So one of these guys is not divisible by pi, so the other is divisible by pi to alpha I, so you get a congruence like this. End of proof. Okay. Okay, this sort of using, using this method and sort of figuring out some congruences. What you get is you get more examples. So for instance, because you had that plus minus, so for one y you get many different, two x's, maybe not many different, okay. That was a bit exaggerated, but you get 2 different x's. So these solutions will come in pairs. So 2025 will come in pair with 3025. So you just need to wait 1,000 years for this to happen next time. And another thing is, you actually will get one degenerate solution of 0,001 if you divide it in half. But this is always degenerate, but you can reflect it and get 9801, which also works. Which is interesting because 1 is always a degenerate solution. So you can also do something like this, and then you get 81, which is the only 2-digit number to satisfy this. Yeah, and basically this way, like for any number of digits, you can reflect 1. So you get 999 blah 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 98, and then you get 0000 blah 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 01. And it always be a solution. If you experiment with this, we did ask some questions about the number of digits of x and y, sort of along the idea of x plus y. If x has n digits and y has n digits, then x plus y will have n digits. So the square will have roughly 2n digits. So sort of everything is fine. But if x has much more digits than y, so if I don't know, if x has n digits, y has m digits, and n is much more than m, then, well, x plus y still has at least n digits, so the square will have 2n digits. But you know that x and y together only have n plus m digits. This is very hand-wavy. Of course, you need to write some plus ones, minus ones over there. But the idea is that the left-hand side, the left part can't get more digits than the right side. And similarly, the right side can't get more digits than the left side unless you allow zeros for the starting digits of y, because then sort of, okay, you can say that y has a lot of digits, but actually the sum will not have a lot of digits. So one example is, you can, well, okay, this is not yet even an example of that. You can have 88209 divided here, and the sum will have 3 digits, but it will be a small 3-digit number, so the square still will have 5 digits and not 6 digits. But x is also, x is a 2-digit number, so it sort of makes sense and like works together. Sort of a bit more extreme example is if you write 28,005,264, and the line goes through here. So the left part is 28, which is really small, and the right part is 6 digits, but it's actually only 4 digits. So the sum of those will have 4 digits, and the square would have 8 digits, as you would expect from this example. So you can play around like that. There was also another question at the end: what if you allow many more cuts? And actually, I did not have any particular observation in my mind about this. I was like, a friend asked me what about multiple cuts, and I was like, yeah, let's add that to the problem. Someone will figure out. And the nice thing you can figure out with multiple cuts is that sort of you want x, y, and z. So again, you can try to write down an equation, something like x plus y plus z. But now you have 10 to m x plus 10 to n x plus, well, the whiteboard is really not going good right now. Something like this. With m probably much bigger than n. So what's an interesting idea is that actually, if suppose that y and z works, I mean, y and z gives you an example, then if you just expand it, then, I mean, this means basically that y plus z squared is, well, I don't even need to write it down here. I can write it down here. This means that this is just 1 plus z squared. And if you just subtract it, then on the left-hand side, you get a difference of 2 squares. You get a nice product for those. X times x plus 2y plus 2z. And on the right-hand side, the only thing left is 10 to m times x. And now you just cancel out the x's. And you get a linear equation for x, which is easily solvable. So sort of from a solution for one cut, you can get a solution for 2 cuts. And I mean, continuing the same way, you can get like any number of cuts, but then your number gets bigger and bigger. But I noted down one example of that. And from our starting 2025, you can get 9, 9, 10, 10, 25. Okay, that was problem 6. I think this is the moment when I'm going to get the charger from my laptop, and I'll be back in a sec for a quick work break. Okay, I'm back. Definitely the whole thing is longer than expected, so feel free to return it after some time. All right. Problem number 7. So in problem number 6, you get a lot of different subtasks, and they had a bit different vibe. Here in problem number 7, I won't bother to solve all the subtasks because I will just present you with the solution to all of them at once. So what was the idea? We basically had some people one of them, and they were arranged in some way, and they wanted to swap places. And how could they do it? Well, one of them was the captain. And the captain can decide that they can swap with a person on one of their sides, but then the crown of the captain goes to the person in the other direction. And at every moment they have they can make a decision to go right or left. To swap right or left. And basically, we want to ask. First of all, can we get any arrangement of people? Second of all, who will be the captain? And those were two subtasks, which you multiply by 2. In the first setting, people were sitting in a circle. In the second setting, you had infinitely many people sitting in a line, but you knew that the situation is not very bad and most of the people sit on their places, only finitely many of them don't. So I will go straight ahead to this second case. Basically, the first case, if you're in a circle, the method for a line will also work on a circle in most cases, because you can just cut the circle somewhere and just pretend that that it's a segment. And this works because most of the ways of most of the solutions for the line were only working within some segment. So somehow we don't have, it's not the full line, and we might need to use the full line in the circle case, but for most of the solutions we don't. Here I probably need to mention that actually it turned out that for n equals 5, the problem gets much more interesting for the circle case, which I did not notice. But sort of, it turns out that n equals 5 is sort of a degenerate case when you can't do much because you just don't have too many people. You just don't have a space to move around. But we'll go to a line. And sort of, okay, what can we do? I will denote, I need to sort of make a notation, I guess. So I will write people as numbers. And I will write a hat for the captain. And on such sequences, we will apply some moves. So the left move is when the captain swaps to the left. No, sorry. When the hat of the captain goes to the left. So the captain swapped with someone on the right, and now the person on the left is the new captain. And similarly, on the other side, you get 1, 3, 2, 4 is the captain, 5. And we will use LNR to be efficient. Okay, so what kind of things can we notice? Well, what happens if we go L and then R? Then R, so we have swapped to F1. And the person sitting in the original in the middle place is again the captain. So what happened is that the captain stayed the same, but 2 pairs have swapped. So if you do it one more time, then the captain will again be in the same place, and the 2 pairs have swapped twice. So that means that L, R, L, R is nothing, which nothing I will denote as identity. Because I'm a group theorist. Okay, but this is interesting because it lets us reverse our operations. So we can actually perform an inverse of L, which will be RLR. And similarly, we can perform inverse of R, which is LRL, which sometimes is useful, but it's also like ideologically it's nice because that means that it's not like you won't be stuck in one position. You can always go back somehow to your original position, which makes the problem much more structured, I would say. What else? Well, actually, so the idea of many people, and my first idea was, okay, we know that most of the people are fine, so we just ignore them, and then we will have some segment on which we will have to work. So if we manage to go around this segment and sort of order the people in the segment, not destroying anything outside the segment, then we will be fine. Actually, it's sort of so what we can do it step by step. So who should go here? Well, we need just to find this guy who should go there, and just put him here. And if we manage to do it without destroying anything, we're gonna be okay. Everything's gonna be fine. All right. Do I want to show all the details? Probably not. But it's interesting to see what happens if you do one of those moves many times. So suppose you have done here, instead of R, you have done L again. So the hat of the captain goes to the right. So it's 1, then 4 swaps with 2. And then it's 2, 3, 5. So 4 has moved to the left, and 4 has moved to the left twice. And you can observe that if you do the L move a lot of times, then 4 would sort of follow the captain. And the order, like the hat of the captain will move, the person number 4 will move, but everything else will stay the same. So the inverse of this move would be that we can do the same, but to the right. So the hat of the captain goes to the right, the person number 4 goes to the right, which is convenient because we can take, if we have, in this position, we can basically choose either the person number 2 or person number 4 because they're symmetric, and then just move them to any step in the sequence. And the hat of the captain moves around with them. And it's so the sketch of how to do something like this is, well, for technical reasons, you don't want the hat of the captain to go outside of the segment. So the idea is you give the hat of the captain to this person. You want this person to go to the left. So you rearrange sort of randomly, so that this person becomes the captain. And then you can do this move, pushing everything to the left, which will be a lot of not L, but R inverses, I believe. And in the end, this person here will, and the captain will be here. So actually, it's not enough because actually you can't get the hat of the captain to the right without destroying the position of this person. But if you just do some little moves around here, then you can actually show, you can actually create an algorithm of how to do it step by step. So that was a big idea. This is not like, this does not give a full solution to this problem, because the problem is you need some space to arrange stuff. So you'll get, basically you can get this sorting intervals shorter and shorter and shorter. But then when it will be very short, then you don't know, I mean, the method doesn't work for around, I think, 5 people. Then once you get 5 people, you can think about it, and it turns out that you can make it down to 3 people, but it's still, these 3 people will have a random permutation, and it's not quite obvious what to do. If you try even more, then you can solve all those permutations of 3 people too, and you can get any permutation of those people, but you don't get a control over the captain necessarily. Who will be the captain? So the answer, I mean, half of the answer of who will be the captain is to finding some invariant. By trying some small cases, you can figure out that actually there is some parity going on. And why? Well, there is some parity going on. So you can observe that if you have your permutation sigma of the people, and the position of the captain is denoted by C, then sine of sigma times -1 to C, this is a number inside +1 - 1, stays the same. What is sine of sigma? This is 1 if sigma is even number of swaps, -1 if sigma is odd number of swaps. It turns out that it's well defined, and you can only have one of these versions for any permutations. Now here we just get -1 to the C. So what happens if we move? Well, we change the sign of sigma by we change the sigma by a swap, so we change the number of swaps by 1, so we get additional -1, and we change C by -1 or +1, so we get a -1 here, so their product will be 1. So nothing is changing in the product. So in particular, in the end, if you have a prescribed permutation that you need to get, then you know what the sign of sigma is going to be like. So you know what parity of C, what parity is C going to have. So it's not like you get to choose where the captain sits. Unless you're back in the circle case, and then you have odd number of people, when there is no such way as parity, because there's no way of defining -1 to the C, where C is a number modulo something odd. All right. So it does not tell as much, but now I will hand wave a bit. What can we do here is, I mean, for sure, if you believe me that we can just try things out, sort things out, and then we get captain somewhere over here, I mean, somewhere nearby, presumably, then the question is why couldn't we just go another way and sort from right to left, which in the end would give us, again, maybe a good permutation, but the captain will be someplace else. So we get 2 same permutations with different placements of the captain. And now comes the idea about inverses. So if it seems that we can do something like this, then once we are in one of those places, we can reverse everything and sort it in the other direction and get captain someplace else with the same permutation. Which means there is a sequence of moves which does not change the permutation, but changes the placement of the captain. And if you can show how to sort things out in these intervals, then this means that sort of you can prove that the sequence exists, even though you have no idea what the sequence is going to be. But actually, it is possible to construct a sequence like that. And I'm not going to write the sequence down, but there is a sequence. So a fact, if you do L 9 times and R 11 times in the correct order, then the permutation stays the same, but the captain moves by 2 places to the right. Which, I mean, probably, I think some people did write a code. Some people just, I think it was possible to figure out by hand, but you needed to know what you're looking for, really. When I was setting the problem, I had no idea if the sequence is going to be there. I was like, okay, maybe there is a sequence like that, and then someone's going to find it, or there is no sequence like that, so there is no sequence like that. And it turns out that the first option was true. There is a sequence like that. Which is, I mean, which was sort of possible by writing down 6 people and then experimenting, like permuting these 6 people a lot, and then you could get something. But yeah, that was hard. Not many people came up with this idea, so for sure it wasn't easy. But that's if you do have the sequence, though, you can solve the problem quite quickly, because you can observe that using this move, basically you can transport a hat to like any other person. So if you want to swap any 2 people, you can get a hat to one of them and then just swap. The hat goes here, the people swap. Then you want to do another swap, you can just transport the hat, and yeah, do a swap, and so on and so on. And because swapping of consecutive people can get you any permutation you want, which is the only place in the world when you should use bubble sort. Do not use bubble sort outside of this argument, please. But then you get any permutation you want, basically. You can sort the people. Some people did not came up with the move that moved captain by 2, but it was possible to move the captain by 4. And then it turns out that because you have those L inverse and R inverse, then actually if you want to swap those 2 people, you can also give a hat to the person over here, and then swapping those 2 and moving captain here is R inverse, I believe. So with a 4, it also works, although then you would need to, I mean, it doesn't answer the full question of who can be the captain, but it is also pretty good, to be honest. So that was problem number 7. And we are getting to the end slowly. Problem number 8. Finally, problem number 8 was telling us about interesting functions, I believe. So we had a set of n plus 2 elements. And we wanted to construct a function, and well, we had an integer c, and we wanted to construct a function so that, well, a function from pairs of distinct elements in C. So that's quite weird. To Z, but actually, I mean, everyone pretty quickly figured out, I think. I mean, if you know modular arithmetics, it could be just Z over N. And we have two conditions. We know that we want that if you do xy and then you do yx and you add those, you're getting C mod n. And well, okay, x not equal to y, and then that f of xy plus f of yz is not equal to f of xw plus f of x f of wz mod n x, y, z, w pairwise distinct. So the first question you might have in this problem is why? And then you look at this second property for a longer while, and you figure out that if you fix x and z, then you're going to get exactly n elements that are not x and not z. So all these sums you can get, you'll get n of these sums, and they give distinct remainders modulo n. So you get all the remainders modulo n. So that's sort of the idea that if you go from x, so I was thinking about it as like the cost of going to somewhere. And then if you go to x, from x to y and back, then you always get the same cost. But if you're going from x to z through another place, then you're always getting a different cost. I should have written this problem like that. It would be so much fun. Well, and the question is, for which n and c you can construct a function like this? Right, so my idea for solving this problem did not work, but I can show you anyway. So, you know, sometimes when you're solving functional equations, then you figure out that if you subtract a constant from your equation, then it still is being preserved. So without loss of generality, you can assume f of 0 is 0. And this is a very useful trick in functional equations. So when I was solving this, I thought, yeah, maybe let's try to do something like this. So what can we do? A transformation that you can come up with is that to every, well, fix your x. And now every fxy will be increased by some d, and every yx will be decreased by the same d for all y. Why doesn't it destroy anything in the problem? Where if we don't have x in here, then we're fine. Well, maybe I should write, actually we have x over there, so maybe fix a and I will do everything for a. All right. Yeah, sure, not all right. Ya. Okay, let's do it in an aesthetic way. I can't complain about people's handwriting and then have a bad handwriting myself. Right, so we do something like that, and okay, if we don't have a in these conditions, then we're fine. If we do have a in these conditions, well, then for the first condition, we increased the first term by a, we decreased the other by a, everything should be fine. And for the second one, if we go via a, then one of those will be up by d, one of those will be down by d. If we start at a, so if a is equal to x, then both sides go up by a, and if z is a, then both sides go down by d. So everything works fine. But this way, now you can fix b, and you can go down with f of ab f of ab by I mean, sorry, I did not. Yeah, I was writing about going up. So we will go up by minus f of ab, and we'll go down with f of ba by minus f of ab. All right, so after this, f of ab becomes 0, and f of ba becomes c. And we can do it for every a, so that we'll have this special b, so that f of ab is always 0 for each a. And we can always assume that there is one element so that f of ab is 0. And I did use it to solve the part b. In fact, that was the main reason the part b was actually a part b, because I thought, yeah, I know how to do part b. I don't know how to do part c. So how does part b work? So what was part b? Part b, well, there was part a first, but people did figure it out. That was about changing c, and that's also like sort of changing your function. So basically the idea was that if you change f by 1, everything, like if you add 1 to every value of f, then c increases by 2. So if you do this the same in the other direction, c can decrease by 2. So you only care about parity of c. Which means that you basically get 3 cases only, which is n is even, c is even, n is even, c is odd, or n is odd, c is, let's say, 0, because you can just, you can also move c by n because everything's mod n, so you can just assume c equal to 0 when n is odd. So part b was about the first of these cases, so c is even, n is even, but c is also even, so without loss of generality, using this movement idea, you can assume c is 0. So n is even. Okay? So now we can assume that there is a b such that f of AB is always equal to 0. Okay, so choose an x, and now I want to write something like f of xa plus f of AB, and we know that fix x here. And by my previous comment, we know that this has distinct remainders mod n. But we also know that this is 0. So f of xa has distinct remainders mod n. And how many of those? Well, there are, well, a needs to be different from x and different from b, so we have n options. So again, we will get every possible option. So this means that there is exactly one a such that f of xa, this is not a great whiteboard, is 0. But what can we say? Well, we also know that c is 0. What does it mean that c is 0? Wow, that was not great of the whiteboard, I guess. What does it mean that c is 0 is that f of xa plus f of ax is 0. So it's sort of anti-symmetric, but that means if f of xa is 0, then if you just compute it in the other direction, then you also get 0. Okay, so what does it mean? For x, we got exactly one a. For a, we got x, but we also know by symmetry that, well, it's exactly 1, so it's also an x. So we get a pairing of a with x. And any element of S outside of B will get a pair, exactly one pair. But also this has n-1 elements, which is odd, which gives a contradiction. So that was a way to solve part B, and I don't think it was helpful with solving the part C. So for part C, I can give you another idea. Part C was figure out all the possibilities here. So for which pairs N and C you'll get some NC interesting function. Okay, so what was the idea here? Well, I will write out of X will be the sum of all f of xy over all possible y. And in of x will be the same, but in the different direction, f of yx. Okay, and what we will try to make sums. Right, so what can we say right now is that in of x plus out of x, this is, well, sum over fxy plus fyx over all possible y. So we get c times n plus 1. Right. In particular, it's a constant, not dependent on x, which is very, very nice. So now I will want to take x and z, and I will want to take the sum of f of xy plus f of yz over all possible y's. Okay, so on one hand, I did make a comment that this gets all possible values modulo n. So this is 0 plus 1 plus 2, blah, blah, blah. Plus n minus 1, which is n times n minus 1 over 2. On the other hand, we'll get basically out of x plus in of z, but not quite. Not quite, because what we don't get, I mean, what we have in out of x and in of z, but we don't get it here, is f of xz. So actually, we need to subtract f of xz twice here, which is actually good, because this gives us a pretty nice formula for f of xz. You can switch using this. You can switch in of z to minus out of z for some plus some constant. So in the end, you get out of x minus out of z minus 2 f of xz equals to, well, now you get this constant c of n plus 1 coming from the change of in to out. You get this constant coming from the sum of 0 to n, but it's a constant, so it's going to be d. Okay, so now I can rearrange it to get out of x minus out of z. Actually, I think from now on I will just write O of z minus d equals to f of xz. All right, but now you can do the same for z and w. And basically, I mean, now it looks like your function is given by some linear function or something like this from these labels of out of x. And if you did try to solve this problem, I mean, if you did try to solve this problem, then you probably started out by checking some linear functions. And it turns out that linear functions are actually the worst possible in this problem. So now we just need to get a contradiction. We get, like, from the fact that this function does not behave like linear function, we got that it actually behaves like linear function. So now what we want to do is get a contradiction. Now we just sum those up. We get that O of x minus O of w minus 2d is 2 of f of x plus xz plus f of zw. And now something interesting happens, because this does not depend on z, whereas the right-hand side, on the right-hand side, this should give us distinct values for distinct z. So what is the only way in which this could happen? Well, if sort of by this multiplication by 2, every remainder gets multiplied to the same. I mean, yeah, you can say that, okay, it can be 0, and it can be 1. So the right-hand side is 0, or can be 0, or can be 2, but the left-hand side is the same. So from this, you'll get that 0 equals to mod n, and from this, you'll get that n is 1 or 2. And now you can check that for n equals 1 and any c, actually any function works, because you want some stuff going on modulo 1, which is not a very complicated thing to do. And for n equals 2, we already proved that if c is even, then you don't get a solution. So it's enough to construct a solution for c odd, and it's possible to do it. Right, and our last thing is part D, which maybe I'm not going to write all of that down. Maybe I'm, yeah. Okay, maybe I'm gonna. Okay, so what was going on in part D? We just swapped plus for minus. And the function in part D were called NC-dual functions, because they were opposite of interesting functions, which I see that we might accidentally force a very pessimistic view of the world, because it turned out that almost no function is interesting. But spoiler alert, a lot of functions are dual functions, and they are actually pretty interesting. So now we know that the difference of xy and yx is equal to c. And now if we take the difference of xy and yz, this is going to be different from the difference of fxw and fwz. So everything just swapped. Okay, what happens here? Because if you swap a plus sign for a minus sign, I mean, you can swap a plus sign for a minus sign modulo 2 or modulo 1, then the examples we got for interesting functions will be also examples for dual functions. So it will turn out that sort of the only interesting functions that are actually also dual. So the concept of the dual function is the proper concept. All right, and what can be done too is basically, well, first of all, nice things to figure out. If you swap y and x around here, you'll get a minus of that. So you get c being equivalent to minus c modulo n. So instead of c being odd and c being even, here we get that actually, again, we sort of will have two options for an even and one option for an odd, but basically we get n0 n over 2. This whiteboard is really sad. So basically, 3 options we need to check is n0 for even, and n over 2 for even, and n0 for odd. And we did have the argument for n0 being even before for interesting functions. And it turns out that basically everything works the same here. So if C is equal to 0, then it means that your function is symmetric. But basically here, the correct idea would be to choose your A, and now you're moving f of ay and f of ya in the same direction. You added them by the same thing. But then again, if you choose your B, you do it for many different A's. You can basically make all f of ABs equal to 0. And then by symmetry, you get all of BAs equal to 0. And then if you write down the second thing, you'll get that actually, if you're away from B, then you'll get different values to different elements. So to exactly one element, the value will be 0. By symmetry, you'll get a pairing. But you'll have odd number of elements, you can't have a pairing. This is very much the same proof as in part B. So I'm not writing anything down because it just turns out that it's impossible. And that was sort of how far people did get in this problem. So I was quite satisfied with myself because I did get more. I did come up with this problem, so it wouldn't be surprising that I got more info. But I want to claim that actually now that's gonna be the proof of the day, really. So I'm going for a purple coloring here, and maybe even like bigger font. Nice. Okay, so what I want to prove is there is a p minus 1 over 2 dual function for any prime p. So in particular, for n equals 2, for n equals 4, for n equals 6, I don't have any idea what happens for n equals 8. No, sorry. I did get something wrong in this sentence. No, I did not. The only thing I did got wrong is that I know what will happen for n equals 8, and I will tell you shortly. But first, let's start with this. So now we want, what do we want? Well, our set has p plus 1 elements. And our function goes to z mod p minus 1. And now the number theorists among you may recognize that actually what's the structure of z mod p minus 1 is the same as if we have z modulo p, but we multiply stuff instead of adding stuff. So my function will go from S with p plus 1 elements to z over p star. And And what does star means? This means that instead of addition, I have multiplication. So instead of subtraction, I get division. So how do I translate my conditions? Well, we want now f of x, y, f of yx to be a constant. What will this constant be? Well, we had like p minus 1, like in additive notation, it was p minus 1 over 2. So it's sort of in the middle of going to 0. So here we'll get something which will be in the middle of going to 1. So something with square 1, but not 1. So this is gonna be minus 1. And now the next part, now that's gonna be interesting. We want f of xy over f of yz not equal to, no, I mean not equal to f of x w over f of wz. I can write it another way, which for some of you might be more known. So if we just do something like this, then we want this to be not equal to 1. And how do we do it? Well, I mean, okay, what it should remind you of? Well, you get 4 points. I mean, 4 elements, sorry for the spoiler. You get 4 elements, and you take some stuff between 2 pairs, and you divide it by some stuff between 2 pairs. And the answer is, of course, is cross ratio. So if you have seen some geometry, some projective geometry over a finite field, then it turns out that the projective line over a field with p elements, whatever that means, if you don't know what a p element field with p elements, don't worry. I mean, if you're scared of fields, don't worry. But if you know what it is, the projective line has exactly p plus 1 points. So that's why our set S has exactly p plus 1 elements. And because we have cross ratio, and if we have 4 distinct points, then the cross ratio will never going to be 1. We win, basically. We get an example of a doubt function by cross ratio. Now, why cross ratio? Well, cross ratio for an easy function of xy equals x minus y. And yeah, you don't need to know about cross ratio or anything like that. You can just define it as a difference. But the problem is, I mean, x minus y, like what's S? What's S? So our set S for now is gonna be, from now on, it's gonna be 0, 1, blah, 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 p minus 1, and then a guy that we denote as infinity. All right. So If x and y are finite, then you define it like that. If they are if one of those is infinite, then you need something else, but something else will not be very complicated. And I think the choice of infinity x equals 1 and x infinity equals -1 should be fine. Maybe -1 and 1, I'm not completely sure. I mean, we can see that because I guess it would be nice to show you why. Why does stuff work? So why does x minus y over y minus z get all possible values if we vary y? Oh no, that should be fine. Yeah. Well, because this is just -1 plus z wait, if we add 1, yeah, x minus z over y minus z. And now the numerator is constant, a non-zero constant, and now the denominator will just be anything you want, non-zero, if you vary y across finite stuff. And you just need to remember that, okay, it can be anything non-zero, so you'll get any number which is not equal to -1. And conveniently, we have defined things for infinity in such a way that if y is infinity, then you'll get -1. And so this is an example of a dot function for every prime p. And yeah, that's basically it. The only thing is that if you know some field theory, then you can make it work actually if P is, some field theory. Then you can make it work for Q, where Q is a prime power. Prime, this should say prime. Prime power, and then you again get a function with parameters Q minus 1 and Q minus 1 over 2. You can also get a function for odd n, which is when you get when your prime power is 2 to the k, then you get a function for 2 to the k minus 1 and c. And in such a case, as we said, this is going to equal to 0. And the idea is basically the same, just instead of numbers from 0 to p minus 1 and infinity, your set S is going to be elements of a field with q elements plus infinity. And basically everything carries through. You just make these operations in this field with q elements, which by some Galois theory, some finite field theory, will exist if you have a prime power. And yeah, then you get a function. Voila. So yeah, in this problem, I actually did not. I do not know what happens for different numbers. So I believe that first. So yeah, also like sadly, no one did actually figure out that this was projective geometry question and that you should use cross ratio. So sad times. But problem I don't know how to solve. So open problem if you'd like to think about it. Well, what about the first example that we don't know what to do with is 5, 0. So, right, because there is no field with 6 elements, our construction will not work. Yeah, and the first thing which for even n, the first thing we don't know is 13.7 and 14.7. Can you build an example for 14 and 7? So yeah, it's interesting because sort of you naturally, if you know where to search, you get examples for prime powers, which do not generalize to any n, like to arbitrary n. But it also means that it's probably hard to prove that 14.7 is not doable. If you know that 12.6 is doable, and you know that 16.8 is doable, what's different with 14? It might be hard to come up with some argument. But again, if you want a research problem that maybe this will be interesting for you, there are some things like this in mathematics. There is a conjecture called AKR, I think. I think K stands for carp. I can't remember really to other people. But if you Google evasive graph properties, then there is a big conjecture about some classes of graphs with fixed number of vertices. And the conjecture is proven for in case your graph has a prime power of vertices. And I believe it's still open for the general case. So it happens sometimes that it's easier to do stuff for prime powers, even if you do basically just combinatorics, which I think is interesting. Yeah, so I think this AKR conjecture, everyone thinks that it's going to be true, but I did once talk with someone about it, and they told me that there was another conjecture that was also proven using similar methods in combinatorics, proven using similar methods for all prime powers. And then people were like, okay, this is just combinatorics. If it holds for any prime power, surely it's going to hold for every number. And then someone found a counterexample for n equals 6. So it can go in many different directions. I would say 5.0 is probably possible to code. So if you have really a lot of spare time, then maybe you should try it out. If you get something, please let me know. I will gladly to hear about developments of this problem. And that is basically it for today, which quite long, to be honest. But yeah, I hope you enjoyed solving the problems. I hope you enjoyed watching this video. Again, if you want to apply to be a tutor, please apply to be a tutor. Deadline's tomorrow. If you did apply as a participant, thank you. Thank you for your applications. They mean much to us, even if maybe the result was a bit disappointing. We really enjoyed reading your materials, and hopefully see you in the future. And yeah, that's it from me. Wow. Goodbye. Why is there? Okay, I think I need to click this button.